Okay, so welcome back to another video. Here we have a definite integral inside our integrand composed of just a function x and in combination with the fractional part of 1 over x and multiplied with the floor of 1 over x dx. So something like this, of course, as you can tell, we'll actually have to utilize the definition functions of formulas for both the fractional and the floor function. So utilizing this, you can also tell that by definition of course, using the floor function, we actually had to convert this integral into a sum of integrals that we're going to add up term by term piecewise. So by utilizing that, and afterwards, it's actually just simply come down to a lot of like algebra and manipulations. That's the fun part, which I personally like myself. So nothing too much that needs to be said. That, of course, we just pretty much just gave the outline, just utilize the definitions for these two special functions. It comes down to a infinite sum that we actually helps me need to simplify in order to get to the final answer we want. So with that, why don't we just jump right in? So let's first perform a nice little u sub. We'll let u equals 1 divided by x, and then I'll let x be by itself, so at least that way we can actually do something to get off the differential by itself when we perform the differentiation. So that means I get that x is then equal to just 1 over u, then simply dx is then just equal to negative 1 divided by u squared, and then du. Okay, so plug this back together, and then don't forget we have to change our bounds that we switch from x to u. So that means if I plug in 1, so that means that's actually just going to be 1 on the top. Plug in 0, so that means that's going to have to approach positive infinity. And so we're just left with, so that means x is going to be 1 over u, then multiply with the fractional of just u, and then multiply with the floor of u, and then multiply our dx differential substitution, so negative 1 u squared, and then du. Okay, then let's further simplify this out such that now we just have to change the bounds again, and then that'll also change that to negative, but that'll get rid of that negative by itself because of that. And so this means we're just left with the fractional, well, first from 1 to infinity of the fractional of u multiplied by the floor of u, then divided by u cubed, and then du. Okay, so we have so far. So let's actually now utilize those definitions, the formulas of the floor and the fractional part. So it's first worth noting that the fractional part of some function x, well, let's just call this u in this situation. Will that be u? So then that's simply just equal to u minus the floor of u. And then, of course, this is being that u is greater than or equal to 0. Then for, of course, now the floor of u for some function u, then that's simply just going to equal to k, such that for u is in between the intervals, so the inclusive of k to k plus 1 non-inclusive, such that k is an integer. Okay, and then utilizing that, so now we can actually just plug in everything back into over here with those formulas we just put in. So then this will then, so I also forget to call this, don't forget to, we'll call this capital I. So then this is going to be for the integral from 1 to infinity. So then the fractional part, so that means I have u subtract the floor of u, then multiply with the floor of u again. We're just taking things one step at a time. So u cubed, then du, then simplify this out. So we're going to write this in terms of, a difference of fractions over here. So then I'm going to have that, this is going to be, so that's just canceled out. So that means that's just going to be the floor of u, then divided by u squared, and then subtract the floor of u inclusive to the power square, and then divided by u cubed, then du. Okay, then next thing we're going to do is now we're actually going to substitute everything for the floor of u for k. And then this being the cases, we're actually going to take this as a sum of integrals. So we're going to write this in terms of an infinite sum. So now this is going to yield us the infinite sum starting at k is equal to 1 to infinity. And then we have that our lower bound is going to be k all the way up to k plus 1 of now simply just k divided by k squared, and then minus k squared divided by, or did I ever say k squared on the bottom? I meant to say u squared. So u squared over here, and then on this one, k squared divided by u cubed, and then du. Okay, then performing the integration itself is pretty self-explanatory to perform. So by doing so, that means I have the infinite sum at k is equal to 1, And then now we have our, we got to calculate our bounds. So what we have now after performing the integration is going to be negative k divided by u. Evaluate this to k plus 1 and then subtract. So now this will be negative k squared and then divided by 2u squared. Evaluate this from k to k plus 1 over here. Okay, close that off. All right, so now after doing all this, so this is, let's see, so we have k is equal to 1 infinity, then plugging k plus 1 and then k for the first, function over here, our first evaluated integrated integral. So then now we have that there's going to be negative k to k plus 1 divided by k plus 1 plus 1, and then subtract. So over here, then this is going to be negative k squared and then divided by 2 times k plus 1 quantity square, and then add this with 1/2. Okay, right there. Okay, so now we actually can simplify this out even further by just first getting this into a common denominator, and then we can actually simplify more stuff out. So after doing so, then we're just left with the infinite sum at k is equal to 1 of 1 divided by k plus 1, add this with k squared divided by, so basically this changes, this still stays the same. Afterwards, we just distribute the negative into everything. So k squared divided by 2 times k plus 1 quantity square, and then minus 1/2. Now that finishes that. So now the next thing to do is, of course, calculate this term over here. So let's move on to a different marker on this one. All right, so moving on, k squared divided by 2 times k plus 1 quantity square. So what to do here is that we can actually change things up a little bit. So the numerator, we can actually write this as the same thing as k plus 1 subtract 1 square, and then divided by 2 times k plus 1 quantity square. Now if I actually expand this, if I expand the top, the numerator out, we're gonna have something nice to say that this is the same thing written as k plus 1 square minus 2 times k plus 1 and plus 1, okay, and then still numerator or denominator still the same thing, k plus 1 and quantity square. Now that means afterwards I could just simplify things out. So that means as you notice, we're gonna have some terms that cancel out, of course. So now I have 1/2, then minus 1 divided by k plus 1, and then add this with 1 divided by 2 times k plus 1 and then square, quantity square. Okay, so with that being the case, that means this can actually be, this piece of the function over here, of our sum right here, can be simplified out by just substituting this back in. So now capital I so far now is going to be infinite sum at k is equal to 1. So first we have that this is just 1 divided by k plus 1. Then we can substitute the simplified form back into here. So plus 1/2 minus 1 divided by k plus 1, and then add this with, 1/2, or 1 divided by 2 times k plus 1 quantity square, and then subtract 1/2. And then as you can tell, we're gonna have some things that cancel out. Basically these two and these two are going to disappear, and then we're just left with this one over here. So therefore, we are left with the infinite sum, k is equal to 1 of 1 divided by 2 times k plus 1 quantity square. And then of course it's worth noting that the 1/2 can also be factored out outside, so we're basically left with 1 divided by k plus 1 quantity square. Okay, so by doing so, now what we're going to do here is, of course, focus on our infinite sum. So k is equal to 1 of 1 divided by k plus 1 quantity square. As you notice, we can actually rewrite things a little bit differently by re-indexing our sum. So what we can do is that we can actually make this into a starting sum at k is equal to 2. So k is equal to 2, and then this will change up to k squared. And then if you actually notice that the function or the sequence 1 over k squared is actually written as in a similar fashion to the Riemann zeta function, evaluated at 2, but that means that we have to actually fix this carefully, because that function or that formula itself actually has to start at the index at k is equal to 1. But since we have that k is equal to 2, we actually have to evaluate the term at k equals 1 first, and then subtract the difference from there. So then this will yield us with just k is equal to 1 of 1 divided by k squared, and then subtract 1, okay? And then, so then I can actually just substitute this back in. So I is then equal to 1/2 times this entire thing here. So 1/2, the infinite sum at k is equal to 1 of 1 divided by k squared, and then distribute the 1/2 to the other one here, so then subtract 1/2. And as you notice, 1 over k squared, k is equal to 1 to infinity, that's actually, of course, Riemann zeta evaluated at 2, aka Basel's problem, aka the value is going to equal simply just pi squared divided by 6. And we can just substitute this back in, so 1/2 times pi squared divided by 6 minus 1/2, which therefore leads to just pi squared divided by 12 minus 1/2, which therefore that is our final answer to our integral that we're being asked to calculate. A combination of just a function, just a simple linear function, with a fractional part and a floor function part. Everything, as you notice, that of course we actually have to break things up in terms of a sum, utilizing the special formulas for that by definition. And then, as mentioned, everything just comes down to algebra, which is used as a simple answer just like that. So yeah, that's pretty cool if you ask me.